Hello, welcome back again. This is the last review video looking at project number 4. Some practical linear algebra seems to be loading up. Give it one more second. Excellent connection at least. And, I'm really thinking about it. Here we go. Seems to be loading up. Give it one more second. Looking good. Cool. Okay, so practical linear algebra for finite element analysis. Finite element is, if you haven't seen it before, it's a general process of like creating structures, like 3D models, and then applying some kind of boundary conditions. Usually it's loads or displacements, and then looking at what are the stresses and strains. But at the end of the day, the main thing that we're solving is we have a whole bunch of forces and we have a whole bunch of stiffnesses. So every one of our elements in here is a spring. Here we have the simplest type of element, maybe not the simplest, because we could also have just a one-dimensional element that doesn't move in 2 dimensions. But for a 2-dimensional finite element analysis, we're using this process called the direct stiffness method to create this stiffness matrix. But each one of these, if I grab node 2 and I pull it upwards, it's going to stretch element 4, element 2, and element 1, and maybe element 3, depending on what node 3 is allowed to do. So the way all of these 7 nodes move, they all affect how much stretching or compressing we have inside this structure, and we can solve for that. We can set up this problem where we have this giant 14 by 14 stiffness matrix, say that times our unknown displacements equals the applied loads, F, and then we can even back calculate, like, okay, if we said certain nodes are not allowed to move, what are the reaction forces there? One thing that I wanted to show, so there's this extra FEA material, which kind of goes into the background of like, what is this direct stiffness method, and like, how do we create this single element link? And this might really help if you were kind of struggling with like, what is this? How does it work? It goes in step by step, like starting off with just this 3-bar linkage that we started, this triangular truss that we started off with in the homework, and building the same ideas from here into the 11-bar truss, almost like a bridge for this project. What I wanted to show here was actually kind of like the real benefits of using AI. So what I'm going to do is I'm going to take this thing and unedited, I'm just going to download this notebook. So it'll take a second, it downloads that notebook, and I'm going to add it into my Module 4 Learning Coach. And, not that, I want this. Go to Downloads, and where did it put it? It put it in my downloads, all right. Downloads. All files. Here we go. Oh no, certain file formats are not supported. So let's see, what is supported? Creating documents, presentations. And I'm kind of learning this along the way too. So it will accept, it does accept HTML, so I could just download it as HTML. That might make the most sense here. Otherwise, I could export it as a Python file too. So let's do HTML. File, download as, and did I run everything? I just want to make sure my HTML is complete. It looks pretty good. download as HTML. Now I'll put this one in the chat. And so the reason that I'm doing this is what is all this? All right, let's get rid of some of this stuff. Get rid of that and this and this. And let's get rid of this too. Okay, cool. Now we're kind of back to square one. And let's pull this one over so we have these two right next to each other. I'm just gonna grab this description, paste it in here. So what I'm doing is I'm giving it some information from the project. I'm giving it all that extra FEA material and telling it a specific task of like, how do I load the stiffness matrix? And this would help me, like for this first part, if I don't know what K is and I already deleted the code to actually load it into my namespace. So this is helping me kind of get to that point. So let's see. Oh, and it's trying to load everything. All right. How would I load it from the saved file in the extra FEA material? Maybe? What? So it's not actually, so down here, it saved it into FEA arrays. Look at the HTML file. What NPZ file saved the stiffness and node information? FEA data. No. It's not really doing what I want it to, right? Data nodes. I mean, it's at least getting a little closer to what I want. Let's try adding it again. How do I load the K matrix from this? So what is it called? And I have had better luck like loading a big file like this and getting more information. I don't know why today it happens to be giving me so much trouble. It's thinking about it. So I'll load it up while it's thinking about that. So we could try this. np.load. And I think it's FEA arrays in the same folder. And let me load up my NumPy. There we go. So now I have like K defined. And let's see if chat actually came into this. There we go. And that's what I just did, right? And then nodes, it even tells me how to get that node information. All right, so now it's kind of getting a little bit more of what I wanted. So nodes, what else can I load from FEA arrays? That's weird. I mean, this is helpful. So I could try this, right? So then it shows me that, hey, look, you have a node, you have an LMs, and you have a K. So we could also load up this value here and say, get rid of that one, LMs. And now I have the elements. So element 1 is made of nodes 1 and 2. Element 2 is 2 and 3. 3, 1 and 3. Kind of connecting all these dots to each other. So 3, 1 and 3, 4, 2 and 4, and so on. These are the main things that you need to start a finite element simulation. Here, a lot of what we're doing is just the solution part. So finite elements, the way that it's split up is usually the pre-processing, which is kind of where you define the geometry, define what materials are involved. In this case, they're all kind of uniform materials with one Young's modulus. We don't even need the Poisson ratio because we're not looking at how much they contract. And then the solution part is the part that we're working on here in this project, where we actually take the information, find all the displacements based on the applied forces and boundary conditions, and then find all the reaction forces based on those restricted wherever displacements are actually defined. Okay, so we're making some progress. And then there was a good idea from the homework of looking at this linal.matrix rank of K. So the rank of our stiffness matrix K is 11. Meanwhile, the size shape of K is 14 by 14. So we're actually three steps short. So it's ill-defined, and that's why I had asked you to look at that condition number, because if you have a really large condition number, there are two reasons for it. Either you have an ill-conditioned matrix, so the rank is not high enough for the number of equations you have, then you have infinite solutions. That's the case if we apply 0 boundary conditions here, but we apply a force, then it could just disappear into infinity. Like it might just start accelerating. And even if we apply opposite forces, on node 1 and node 7, we can still have rigid body displacement, which doesn't help us solve one problem. We just want to get one solution rather than coming up with a problem with infinite solutions. And then kind of take this, paste it down. If we compare that to 2 through 1, 3, 2 through 1, 3, now we have an 11 by 11 matrix with a rank of 11 and condition number of 52. Much more solvable problem, where even when we go through all the math in this, we might lose one significant figure. So if we think about like what error is involved in this, we could say 52.23 times 10 to the negative 16, and we end up with an expected error of about 5.2 times 10 to the negative 15 if we're using that same kind of homework solution. Or we could use the actual like np.finfo float of .eps, call that my accuracy, and it's still 10 to the negative 14. Here it's like 1.2 times 10 to the negative 14, like what error we would expect from that, versus up here we would expect kind of 10 to the 1, 10 to the 2 error in this solution. And sometimes it'll give us a solution, other times it'll say like, hey, like in this case, it can see that the rank is not high enough, and it probably won't actually go through the calculation. Okay, so then moving on to the actual solution part, most finite element methods do use some kind of LU decomposition, and then when you go to resolve, if you change some parameters and resolve it, it'll reuse that LU decomposition to save a little bit of time. But we don't, if you want to define your own LU decomposition, in this case we don't need any pivoting. It's a nice, what is this? It's in this case it's full rank once we account for those boundary conditions, and it is something else. Maybe it'll come to me later, but full rank positive definite. It's a full rank positive definite solution, and it doesn't really need pivoting. It's well behaved. So for this, it's kind of a simple linear algebra problem. So we're gonna say our K, we'll call it like solution, is K of 2 through 13 and 2 through 13. F is, we'll call it zeros of, I'll say 11. I'm gonna hard code it as 11 because I know that's what I want here. I could say length of K to try to match it, but I'm gonna do this. And then F of 5 is negative 300. This part, I think some people got a little confused of like, is this all of the F values, or is it only the applied force values? In this case, it's the fifth index 5 of a length 11 vector. So it's not including these first two values. If you do include those first two values, I think it applies the force somewhere down here because it's off by 2. So this is, in this first case, it's xy of 1, xy of 2, xy of 3, xy of 4. So 0, 1, 2, 3, 4, 5, 6, 7. So this would be, if you wanted to have this be the full thing, this would be number 7. In our case, since we're excluding that one, we start here and say 0, 1, 2, 3, 4, 5 for that downward applied force. So now I've got F, I've got K, and just to check that we're doing everything right, dot solve of K solution, F over E over A, and we'll say E is 200 E3, A is 0. This is in megapascal, and this is in millimeter squared. You can use other units if you want. This is kind of a unit agnostic, like it doesn't care what units we want to use, but our K matrix is all in 1 over millimeters. So if you're going to change the units, first you would have to change this to 1 over whatever, micrometers if you want, or meters, or feet, whatever values you want to use, inches, and then convert things back. So I like millimeters and megapascal because 1 Newton per millimeter squared is 1 megapascal. It's just a nice consistent unit, and especially here, works out pretty well. So let's see. We get some values. They're all kind of 5 to 16, which makes sense to me. So at least I'm doing something right. And let's grab this, put it down here, and we'll add a time it, and then we'll come back to it. I didn't ask you to time it, but we'll just give it a shot. So that was about 30 microseconds. Again, as an engineer, whether it's 30 or 40 microseconds, it's still, to me, instantaneous. So it's not a big deal. But for best practices and kind of learning the ropes of numerical methods, let's compare that to an actual LU decomposition. And for that, let's add from scipy.linalg import LU factor and LU solve. I'm doing this because I saw a lot of people kind of piecemealing LU factorization and LU solution methods. This LU factor and LU solve works really well. It's really fast. It's a great way to store that LU factorization and the pivot matrix. So if you're going to use kind of piecemeal stuff, then use import the right tools. Otherwise, if you want to dig deeper and try building it yourself, start off with the code from this LU decomposition, and you can go from there. So I don't, at least in this reading, I don't even get into pivoting because it's something that is done really well in a lot of places, and there's no reason to kind of recreate it. It's good to know how this LU decomposition and Gauss elimination kind of work in a simple case, to look at that code, because there's not as many for loops and comparisons, and things don't get as complicated as quickly. But if you jump into this LU code or that LU factor code, there's more stuff going on, more checks and balances to make sure that it works for all different kinds of reasons. So if you're gonna make it more complicated, let's use something that's already done pretty well. So let's say LU factor of K solution. Oh yeah, and we should say this is our LU and pivot is that. And now I can say LU solve of, I think I do this, and then F over E over A. And I get the same answer that I found before. 16 is my max, my minimum is down here at 0.7, but 5 to 16. So let's look at this. Percent, time it. And I haven't tried this, so this is new to me as well. So before it took 30 microseconds, and now it took 7 microseconds. So even in this, we didn't have to do any pivoting for this one, because if I look at what the pivot matrix actually is, it goes 0 to 10. It's not switching any of those rows. So it's very efficient to store this matrix in this LUD composition and then start running it from there. And that's why finite element softwares will do that in the background. We don't really see it most of the time. We're kind of focused on like the overall structure and things like that. But it's kind of cool to know like where do these speedups come from, and that's part of this class, is learning a little bit, just enough so that you can ask the right questions when you're doing more numerical method kind of stuff. Cool. So it works. It works really well on this little 11 by 11 solution. Okay, so now we've got that. We can say our U, let's call it U free, like all of our free solutions for displacement. Are these, but I also have 2 more displacements for the X and Y on node 1, and then 1 more at the end for node 7. It can't move up and down. So in total, if I call this like U total, is NP zeros, 14. And again, here I'm hard coding this because I want to kind of manage where things are going myself. I could say that it's the length of K, like the big K, but I don't want to do that, at least not for now. And then I'm going to say 2 through 13 are equal to U free. And then let's take a look at U total. Now I have length 14 vector of every displacement. There's a 0, because node 1 can't move left and right. It can't move up and down. Node 7 can't move up and down. All right, cool. Now I can get to the cool part and say, what are the reaction forces? So EA times K at, so the at symbol is going to be multiplying that U total. And I end up with, here it looks like a bunch of numbers, like there's a whole bunch of forces applied, but take a look at these 10 to the negative 14 values. And remember, the best case scenario is our error is 10 to the negative 14. So everything with that negative 14 is a 0. And there's no difference between this number and 0, because that's how much error we would expect from this 11 by 11 solution. So the only things that don't have that, I mean, there's a negative 13. That one's also basically 0, just a little bit extra floating point, or like round off errors or whatever. But we have a 1.5 E2, so 150, and then we have 150, node 1 y direction, node 7 y direction, and then this negative 300, that's the one that we applied at node 4 in that y direction. So 150 plus 150 equals 300. So sum of the forces equals 0. This is our total, like F, we could call it like F applied. Yeah, something like that. F applied. So now, really what I want is something like this. I want to see what are all the displacements and all of that. So I'm going to try giving Copilot something. I defined my node displacements as, and let's do this. Just to tell it that this is definitely Python. And my forces as me write a matplotlib. Help me create a matplotlib figure with all the forces and displacements shown as arrows and the undeformed and deformed truss included. And let's see what this one comes up with. So in this extra FEA material, I created like this. So if you define U as this and F as that, we can use this. And just to show like how I would change this around, let's just try it out. Let's give it some F. And oh, it doesn't have that IX and IY yet, so I'll have to go in and define those. And that is defined up here, going a little bit further up, IX and IY, like that. And let's give it R, because I think I saw R in there too. I could put it as part of that function, but I'm going to leave it right there. L is not defined. Oh my god. Okay, there we go. So now if I change this to 5, it'll give me like a 5x deformation scale. And I grabbed this code because the R was missing and that IX and IY. It's one way of post-processing these results. And let's see. Add displacement arrows. Let's see. Rightful plotting code. Loading the nodes and elements. All right. And here I'm just kind of interested to see what this is doing. Because some of this stuff is not actually defined by me. So let's give it a shot. I don't need any of this, right? Because I already loaded all that stuff. So let's get rid of it. I don't want this. I already did that. I already did this. And so as you're kind of looking, so if you're using AI, kind of like here, where I'm copying stuff over, you should never have like this same code written twice. Like you just don't need it. It's already in. It's called the namespace, like the list of things that I'm allowed to use in this time while I'm using Jupyter. It's already defined. I don't need to redefine it. So just do some trimming. Don't just keep copying longer and longer blocks of code, because already this is kind of hard to interpret what is happening here. At this point, I'm trying to see, is it doing what I want it to? Maybe. Let's give it a shot. elements is not defined. Let's see, where is elements? Control F, elements. For E in elements, I think these are going to be 1 and 2. I don't know what it thinks the elements are. 1, 2. Deformed nodes. I don't know what it thinks the nodes are either. I'll try copying it since I'm copying the nodes up there. Yeah, why am I doing an ax.plot if? I don't think I need that if statement, right? I don't want that. I don't want these if statements. I don't know what they're doing. So I'm just gonna get rid of them. Index 7's out of bounds. Now, why is that one out of bounds? Let's see. What does it think my nodes are? So here it's giving me a 3. Somehow it's adding like deformation to the actual node definitions, I think. So I think this should be a 1, that should be a 2. So now 1, 2, 3, 4, 5, 6, 7, and then those are being added. And then I think same thing here. These should be 1s. These should be 2s. A 1. A 2. I had a feeling that was going to be the case, but I wanted to just see what happened if I just try to run it. So node 7 is still out of bounds. So plot the deformed truss. It helps to split things up a little bit this way. Node 7 is out of bounds. When are we getting to node 7? In elements. For E in elements, nodes. Yeah, why is it grabbing? Oh, so this one should be. Shouldn't this be nodes of E0? Oh no, it should. Alright, never mind. Alright, let's look at this. LMs. No. So LM1. There is. Oh, here's node 7. Oh, -1. We're an off by 1 error. That's why. So I could subtract 1 from everything, and that would get us back to the right value. So let's do that, since we have this, since we're doing this anyway. and then we'll merge this one back into here. Shift M, merge it back together. And you're just watching me struggle with AI generated code now. Too many values to well, at least it got through this one. It plotted it plotted this one, okay. And what's your problem now? Add displacement arrows. Let's see. It is too many values to unpack. Probably because we only want, scale displacement, U total. Let's see. Let's do this of all the rows, but start at the second column. And let's see what that one looks like. Is it supposed to be deformed nodes or nodes? This one's nodes. U total 2I. All the rows start at 1, go to the end. So now I get 2 values for I, xy in enumerate nodes. Let's just print it. Print I, xy. That one seems to work, right? Oh, I guess I have to do the same thing down here, right? For I, xy. That one. All right, we're getting closer. It's not great, but it's much closer than when we started, right? Scale forces. Let's scale the forces to 1. And then what are these displacement scales? Scale displacement. Oh, 100. Oh my God, that's way too high. Let's try 2. Oh, look at that. That's not bad. I don't love the legend, so let's just get rid of it. And now I have something that looks pretty close to what I was going for. It took some finessing, definitely a lot of garbage code that just got thrown in there of like AI just saying like, oh, maybe you want this, maybe you want that. That part gets a little annoying. So definitely do some trimming. You got to trim things down. And then the nice part about Jupyter is you can split things up and then you can merge them back together. Oh. So Shift M, Control Shift minus. There's also this like cell or edit, split the cell. Then there's like merge cell above, merge below. So you can start combining and removing stuff. Okay, so and all of this was for steel. So works. It does exactly what I had done before, slightly different like sizes for stuff, but you could go in there, kind of change what these things are. And now coming back to, so U total, max displacement was 16 millimeters. But I want this number to be 0.2, kind of trying to get down to this cross-sectional area. And if you were trying to figure out like how long are these, they're all 300. These are all equilateral triangles. They're all 300 millimeter long triangles to try to figure out like what's the final weight. You can report weight in grams or kilograms. You don't have to convert. I know that technically grams are not a weight, but they are across the board, if someone asks you how much does that weigh, if you say 5 kilograms, they know exactly what you're saying. You don't have to convert 5 kilograms to 48 point something newtons. Nobody knows how much a newton is. They have to kind of mentally calculate, like, okay, divide by 10, it's how many kilograms. So weight is, you can report newtons, but it makes more sense to do grams or kilograms, something like that. So if I want this 16 to be 0.2, I need to change how thick these things are. And the main way that I got to that deformation, kind of scrolling back through all of this, I didn't need this total thing. All I really needed was this, just this one line of code. So here I have that 16. I could change this instead of 0.1, try doubling it. If I double it, it changed which ones. So let's go to number 5, because that's the one that I cared about, right? So 0.1, there's my 16. So if it's 0.1, it's 16. If I double the area, look at that. It's exactly 1/2 of what it used to be. So we could use that linear property of, like, if we know one deflection, and this is what we saw in the, hopefully you kind of notice this in the homework, that as you look at that truss, let's see, did I make a plot? No, I guess I didn't make the plot, but in your plots of this truss of, like, as you keep increasing this force, this reaction force was linear. It was directly, it has a slope, like it's not that 10 newtons here is 10 newtons there, like it might be a factor of whatever, 1/2 or something, but there's a direct factor. If there's 0 force, there's 0 P1. Same thing here, because we have a linear algebra problem, everything scales linearly. That's why we call it linear algebra. So I could say for this, like, so there's my, like, negative 16. If I divide that by that 0.2, I could call this my new, like, A desire. And let's take a look at what this is. And did I do everything right? I feel like I did something wrong, since it's not quite, because it's 0.02. It's 10 times smaller than what I wanted it to be, right? Times 0.02? Times 0.2? I'm missing a factor of 10 here, right? But so one of the reasons that I'm doing this is, like, yes, you can use any method you want to figure out, like, what area. Oh, duh. 0.2. Yeah, 0.2. That's the desired. You can use any method you want, but at the end of the day, you have to show that your displacements are actually what you wanted. So in this case, I'm gonna say divide by 10. Or maybe, like, yeah, that's weird. Why am I getting that factor of 10? I'm off by a factor of 10. I'm sure if you're working on it, you can figure it out too. But I'll leave it at that. So the main thing here is that this 0.2 millimeter is the 0.2 that I was looking for. So my A desire is now, like, oh, we'll do negative, so it's a positive. And really, I would print, if I was doing this, I'd, like, putting a little more effort in, at least for the next problem, right? Paste it down there. I would want to pretty print this and say that's 8.06 millimeters squared, and then look up the, I think steel is No, aluminum is 2,700 kilogram per meter cubed. Steel is more. Oh my god, I should know this. Steel density 8,000 kilogram per meter cubed, or 8. You can use grams per centimeter cubed if you want, but then you have to convert centimeters to millimeters. But somehow units got to work out, right? But whatever area I choose, I say like this is the area. That's our design. That one, it needs to be the right. I need something to show that it's the right one. Okay, so this is the last video for ME3255 for this winter session. I'll take, as we're coming into go into our courses, 3255, just kind of a wrap up of things. Go back to student preview. So make sure you do this participation like a self-assessment that helps me understand like how you are interacting with the course. Then as we kind of look at this calendar, I like the month calendar a little better. I don't love either of the calendars, but this one's slightly better. Anything that gets in by the 18th, so over the weekend, I probably won't be able to give comments and things back. I'll give comments on project number 4, but all the revisions that are coming in, like 17, 18, I won't be able to like give some comments. So I'm just going to give grades and calculate final grade. I'm here for any kind of Python numerical method questions that you have like in the future for other classes or design projects or future work or whatever you want to do. You got a friend in Python here, and I can always try to connect you to other people in the Python world. So that's how we wrap up this little workshop here. Like, make sure you do this assessment, check your gradebook, make sure that everything has something submitted. Here, as a student, I'm lacking. I haven't opened anything and nothing's been graded. Make sure everything's graded, make sure the grades kind of make sense to you. And then on Monday, I'm gonna scroll through everything, make sure you have credit for all the work, and then submit grades. Okay? Have a great weekend. Thanks so much for all of your hard work. This has been really awesome to see how much you've progressed in these last, really it's like 2.5 weeks, because New Year's and New Year's Eve really threw us off. Like, it accelerated everything. Every day we did something new. Every day you rose to the challenge and tried something. So you should be very proud of yourself. This was great. I'm proud of you, and I hope to see you